Okay, we have 2 more minutes. Maybe we start in 2 minutes time. Okay, I think we are about to get started. Let's shrink the window. Yeah, hello everybody. I hope everything is okay with you. And you guys did relatively well in the last take-home exam. Screen sharing has stopped. Well, why did that happen? I have to go and open the window again. Yes, can you see my window, my screen? Hello, everybody.
Yeah, we can see your screen.
Okay, very good. Let me begin then, because there's always this hiccup when I try to share the screen because it doesn't show very much from my side. Let me see. We are going to talk about waves in layered media today, which is a very interesting topic because there are many occasions where you can actually make use of this knowledge in engineering and electromagnetics. And we are going to take a shortcut to understanding this area. We're going to use transmission line theory to help us understand this subject matter more expeditiously, because most textbooks would deal with this topic in a rather complicated fashion. But I'm going to use transmission line theory, which using a technique called analogy, or math homomorphism. In the last lecture, we showed that if we have a single interface reflection problem like what I have shown here, okay, you have a wave coming in and reflected and transmitted, and that with proper scaling of variables, you can show that this problem is actually homomorphic or analogous to a transmission line problem with a single junction. Okay, and if this is Z01, this is Z02, we know how to write down the reflection coefficient between medium 1 and 2 using transmission line theory. So it was something like Z01 minus Z02 over Z01 plus Z02 kind of thing, okay? But this analogy can be used to solve more complicated problems. More complicated problems involving waves in very complicated layered medium like what you see on the right-hand side. So what happens is that when I have a problem like this and then I add a layer behind it, I know that the wave will get multiply reflected, transmitted, and then there will be multiple reflections and so on in this layered medium. And it turns out that this seemingly more complicated problem can be replaced by an equivalent transmission line problem of this kind. You have a middle section and then another section, an infinitely long transmission line, Z03. We already learned how to solve this problem. We already learned how to solve the multi-section or multi-junction transmission line problem. Okay, and we can use this to help us solve this problem. So let's revisit this problem then. What we found was that we have some kind of a generalized reflection coefficient, and the generalized reflection coefficient was given by gamma 1, 2 tilde, which is a reflection coefficient including multiple reflection from the background or behind the first junction. And then we derive this recursive formula. Let me write this LZ over 1 plus gamma 1, gamma 2, 3, tilde e to the minus 2j beta 2ZL2, okay? So what we do then is that if we have this problem, and if this length is L2Z, L2, okay, if this is L2, and then if the wave number in this region is beta 2Z, okay, beta 2Z, and then the wave number in this region is beta 3Z, and then the wave number in this region is beta 1Z. We know how to solve this transmission line problem. And the derivation is kind of long, but it's given as a homework problem for you so that you can actually derive this formula. The important thing about this formula is that it's a recursive formula. Gamma 2, 3 is the reflection coefficient at the 2, 3 junction. This is 2, 3, 1. Okay, this is 1, 2, 3. At the 2, 3 junction, we have a generalized reflection coefficient. You can work recursively backward and find the generalized reflection coefficient at this junction. And this formula says that you can keep adding layers at the back, it doesn't matter. You can keep adding layer at the back. And once you know how to find this reflection coefficient, say if I add a layer 4 here, if I know how to find gamma 3, 4, I can use this formula, work backward to find gamma 2, 3 tilde, and then work backward. And then until I found the reflection coefficient at this junction. This is an extremely powerful formula, okay? And I'm going to apply this formula for a layered medium, that if I have, say if I have a layered medium, and then the layered medium can be very, very many, okay? So if I know how to find the reflection coefficient, say if this is region 1, 2, 3, and so on, this would be the reflection coefficient at the 1, 2 interface. And then I might have a local reflection coefficient at the 2, 3 interface, and then I will have another reflection coefficient at 3, 4 interface, using the same technique, using mathematical homomorphism, using mathematical analogy. I can write down the generalized reflection coefficient at this junction. Okay, it will be given by the same analogy, because we show that the transmission line problem does map to a single interface reflection problem. We can actually map the Maxwell's equations through to transmission line equations or the telegraphist equations in a previous lecture. So I can actually write this as 2j beta 2z. Let me call this L2. Okay, let's call this thickness L2. And then I can also write down the denominator using analogy, entirely by analogy. So that allows me to find the generalized reflection coefficient. At this junction, I want you to distinguish between generalized reflection coefficient and local reflection coefficient, okay? R12 is the Fresnel reflection coefficient. R12 tilde is the, what I call a generalized reflection coefficient. Okay, by using this formula and with the knowledge of the local reflection coefficient at every interface, you can find the generalized reflection coefficient at any of the interfaces in this problem. Is this clear? Is this procedure clear? Any questions regarding?
I had a quick question.
Yeah, sure.
So in order to solve this, we still need to be able to solve for one of the reflection coefficients at the very end of the chain, correct?
Yes, yes. Yes, you can maybe go to the last one. This might be Rn plus 1 at the end. And then you recursively work backward, because you can plug this formula. If you are at the last end of the chain, the last reflection coefficient will become a local reflection coefficient, or the Fresnel reflection coefficient. So you recursively start from the back and then work backward until you find the generalized reflection coefficient at the 1-2 interface. So you do need to know the local or the Fresnel reflection coefficient at every interface. Okay, and once you know that, you can build the system up recursively to find the generalized reflection coefficient at every interface, and hence at the first interface. Is this clear? Are there any questions regarding this procedure? Okay, if not, then we can move on. And this represents a very powerful way to solve for the solution or reflection of a wave from layered medium. Layered medium is very useful. For instance, the Earth can be considered a layered medium approximately. And there are many microwave structures that are made of layered medium. We have Fabry-Perot resonator in optics. Okay, and you can use this to make filters. So the wave would propagate through this layered medium, and they will be constructively interfering and destructively interfering with each other. And by choosing the layering, you can get the wave to transmit or not to transmit. And hence you can have filters. If you look at the transmission coefficient, it might look something like this. So at certain frequencies, wave can transmit and cannot transmit. And all this can be done by engineering design, okay? You can also do this for microwave, as well as in optics. And here's just an example, another example of the picture of a layered medium that I take out of Kong's book, okay? And most textbooks do not treat oblique incidence, but I treated them in the lecture notes. And if you look at Kong's book, he treated the case of normal incidence on this layered medium. They can show that you can map this problem into a transmission line problem quite easily, because you can show that the intrinsic impedance is mapped to the wave impedance. You probably remember that we have this wave impedance, which I call omega mu over beta z for TE, okay? And it's omega epsilon over beta z for Tm. Okay, I might have remembered this formula wrong, okay? But this wave impedances are, maybe I have it the other way around, okay? For Tm, it might be this way. Okay, what happens, you should notice, is that this wave impedance actually becomes intrinsic impedance when you have normal incidence. If you put omega back here, it will be beta minus beta x squared, okay? And for normal incidence, beta x is equal to 0 for normal incidence. And then you will have omega mu over beta again. And omega mu over beta is omega mu over omega mu epsilon. Okay, this wave impedance will be equal to mu over epsilon, which is also called the intrinsic impedance of space. Okay, wave impedance becomes intrinsic impedance, and for this problem, they just map to intrinsic impedance of spaces, and it's quite easy to do. Any questions regarding this? So next time, if I give you a layered medium problem, just think transmission line, and you will get the answer right away. Okay, any questions? If not, then I like to go to the case of group and phase velocity. And let me see. I don't have, but I like to talk about group velocity. We already talked about phase velocity. We said that if we have a time harmonic signal, then the wave propagates maybe with a complex in this manner, and then you can did I get disconnected again? Okay, so you can actually look at this in the time domain by taking the real part.
We can't see your screen anymore.
Oh, screen sharing stopped. Let me see. Thanks for letting me know. Let me try sharing again. And can you see my screen?
Yeah.
Okay. Sorry about that. I don't know why that happened. So you can actually obtain a time domain version of this phasor signal quite easily by taking the real part of the above. And that will give you something like V naught magnitude cosine of beta xx minus omega t plus a phase, okay, because this is a phasor, so it has a phase. And you can see that beta x is related to the phase velocity, so beta x is omega over v phase, or you can also say that this will be a function traveling with a phase velocity, which is omega over beta x. So it's quite easy to see what the phase velocity is. It is related to beta x. When you convert this back to the time domain, and you can see that this is the traveling wave. But then when you have a beta x that is a rather complicated function of omega, then different frequencies would travel with a different phase velocity, which means that if you have a multi-frequency signal or non-monochromatic signal, then this will have multi-frequency components, and different frequencies would travel with a different phase velocity. That would be bizarre, because if you start them out all traveling at the same frequency, same velocity and so on, they will run out of phase with respect to each other after a short distance of travel. So that is not good, which means that if you try to constitute a wave packet, say if you have a wave packet, it is not a monochromatic signal. And in the beginning of time, they have Fourier components. There will be this component plus this component plus that component. And each of the Fourier component of this wave packet will travel with a different phase velocity if beta x is the function of frequency. That makes the traveling of this wave packet kind of bizarre, and you cannot describe it with just the phase velocity. You have to use the concept of group velocity to describe the propagation of the velocity of the wave packet. And I can give away the answer because you probably have learned this in your undergraduate course before. The group velocity is d omega d beta x instead of just that, okay? It is a narrow band with concept. As you can see, the derivation, it is only valid if the signal is narrowband. If the signal is very broadband, there's no such a thing as a group velocity. Okay, let's see how we can see this. So if we have a CW signal, which is also called monochromatic, depending on which field you're in. In optics, we call it monochromatic. In microwave, we usually call CW, or it's a time harmonic signal. This is also used. We can represent the signal in the frequency domain quite easily. We can say that, let me use z-axis to represent the direction of propagation now, okay? That if you have a signal in the frequency domain, you can write it quite easily as such a thing. Let me use K, okay, because I use K in the lecture note. K and beta are interchangeable in this course, okay? Some optics people would like to use K, microwave people would like to use beta. And you can quite easily show that in the frequency domain, that the wave equation to be satisfied by this signal is this Helmholtz wave equation. Okay, and we have derived that before for a component of the electromagnetic field like the E field, and I can call this to be my K square, which is a function of omega. And then I could then Fourier transform this signal, and say that V of ZT, I'm not going to use under tilde to represent this. Previously, I just used under tilde to imply that these are complex signals, but I'm not going to do that. I'm going to assume that you understand my notation. And I'm now just doing a Fourier transform, okay? And this is how you do things rigorously if you're a mathematician or physicist. And if you're an engineer, you use a phasor technique and get the solution in a time domain. But to be rigorously correct, you're supposed to sum over a broadband signal in the frequency domain. To go to the time domain, okay? Even though I didn't talk about Fourier transform in this course very much, I gave some homework for you to do so that you can understand what this really means. Fourier transform technique is very, very similar to frequency domain technique, okay? I'm going to assume that this is going to be narrow band. It's going to be narrow band so that I can define a group velocity for such a function. For instance, if I have a function of time that looks something like this. Quasi-monochromatic, maybe I draw something that looks almost like monochromatic signal, okay? Let me assume that it almost looks like a monochromatic signal, but not quite, okay? It has a beginning and it has an end. And if you were to Fourier transform this and look at what it is like in the time domain, in the frequency domain now, sorry, it will have a narrow bandwidth. This is its Fourier transform. And one thing good for you to understand as a good engineer is that the Fourier transform of a Gaussian is a Gaussian. So this is a Gaussian shape function. Once you Fourier transform it, you also get back a Gaussian shape function, okay? Ft of a Gaussian is a Gaussian, okay? So what I'm trying to say is that if this is narrow band, this is something that is centered about DC. In general, the bandwidth does not have to be centered about DC, okay? It can be centered about certain center frequency, and the bandwidth of the signal can look something like this, okay? Okay, so actually I have a wrong diagram here. That should be narrow band, so I shouldn't fill it in with something in between, okay? It will look something more like this. If you to Fourier transform this, you will get something that looks more like this, okay? Not something filled with sinusoidal function in between, just that. So one thing good to remember is that you have to have all this concept of Fourier transform theorem at the back of your hands. So you can think of, if you would do Fourier transform a sinusoidal signal, what do you get? Does anybody remember if I have a pure sinusoidal signal? What does it Fourier transform to?
2 direct deltas.
2 direct delta, very good. Okay, depending on whether it's sine or cosine. Okay, you get 2 direct delta functions. Okay, so if I have something that looks like that, in the frequency domain, it will look like that. So now you can use some very simple theorem, this is T, that if I were to shape this function, a sinusoidal signal with a Gaussian pulse, okay, what would this Fourier transform be like? Well, there's one Fourier theorem that you have to remember. If you multiply something, I can get from A to B with the multiplication. I can multiply A with a Gaussian pulse, a Gaussian shaped function. I will get B. And if you multiply something in the time domain, what are you supposed to do in the frequency domain?
Convolution.
Convolution, very good. But what is the, so you take this thing and take the Fourier transform of the envelope, okay? So this thing transformed into this, but this thing transformed to a Gaussian. As I said before, Fourier transform of a Gaussian is a Gaussian, okay? So what you need to do is you need to convolve this, the third figure with the first figure. When you convolve them, you get this. Okay, so roughly the Fourier transform of a wave packet looks something like that. Does everybody get it? You can work this out very quickly in your head without having to do things in detail if you remember all the basic principles of Fourier transforms. Any questions so far? So what I'm trying to say is that if you have a wave packet, its Fourier transform will look something like this. Okay, its Fourier transform will look something like this. And then you can quickly work this out in your head as to what it should look like. So let me look at the wave packet. Let me move this up here, okay? And it will look something like this as a function of time. It will have a slowly varying envelope. And then it is that envelope multiplying a sinusoidal function that gives you this shape. And I like to analyze the velocity of propagation of this wave packet next, okay? I will call that the carrier and then the slowly varying part of the envelope. So I'm going to do some Taylor series expansion. And as I said before, in the frequency domain, or in the Fourier space, this was written as this, e to the minus jkz. And I'm assuming that the signal is narrow band, so I can approximate this k. K is usually a function of omega that is rather complicated, okay? For instance, when you have a surface polariton or surface plasma polariton, that beta x is something like omega mu epsilon 1, or maybe epsilon 2 over epsilon 1 plus epsilon 2 kind of thing. This is SPP. So that k, which is kx in this picture over here, is a rather complicated function because epsilon 2 is a plasma. Okay, so in general, when you have a guided mode on a structure like a SPP or waveguide mode, that beta x or that k is a rather complicated function of omega. But we can still analyze what its group velocity is by doing a Taylor series expansion. Okay, so even though k is a complicated function of omega, by doing Taylor series expansion, I can say that it is omega naught dk omega naught d omega. This is just the first term in the Taylor series expansion. And then I can take the second term in the series Taylor series expansion. I will have this as my dot, 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 okay? So I'm going to plug this back in to get the time domain signal. Okay, what I should have then is that okay, what I should have then is that I plug it back into the previous formula to get the time domain signal. I'm going to plug it back here, back into this formula. Let me see if I can make it bigger. Okay, I'm going to plug it back here after having Taylor series expanded K, because this integration is only going to be over a very narrow bandwidth. So K is going to assume values of omega that are very close to omega naught. I'm going to approximate K around omega naught by this function on the right-hand side, which is a Taylor series expansion. Plug it back in here and collect terms, okay? So plug it back in there and collect terms. And then I will find that V, Z as a function of time now is, and I can do the detail for you, but you can also do the detail yourself, okay? Plug it back, collect terms, and then if you collect terms, you're going to find that you're going to have a constant term coming out like this, and then you will have this term being a constant can also come out of the integral. Okay, and then what you have left inside the integral is these terms that are depending on omega. And then I will have V naught of omega in there. Okay, and then I will have the exponent e to the j omega minus omega naught t. And that's the trick I did here. Okay, and then I'm going to keep this term in there. Okay, let me see. I'm going to keep this term in there. If I put this term in there, it is going to be something like j omega minus omega naught dk d omega. I'm going to have this term left, and then there will be a z. Okay, I'm going to plug in my z. So you see, by collecting terms, I deliberately, oh, it says my internet is unstable. Let me see if it's okay. Okay, can you see me and can you hear me?
Yeah. Sorry, your speech is very smooth.
It's good? Okay, very good. So can you see this? I plug this in here and then plug it back into this expression over here. Okay, plug in this expression, collect the first term, put it outside, and then I plug in an omega naught here deliberately, and then take it outside again. So in essence, I'm adding and subtracting term. And then I plug this term here, okay? So what I have left in the integrand is this. But V naught is going to be narrow band. I only need to integrate this over a very narrow bandwidth of frequencies, okay? So I can see that if I look at the complicated expression here, it's actually a function of t minus the k over the omega c, okay? This is common to both. So if I were to look at this function, if I factor out this and look at this function, this Fourier transform function is actually a function of t minus dkz d omega. Can everybody see that? You take this outside, I can collect these two terms. And if we collect them together, is a function of t minus dk over d omega z. Okay? And then it's a Fourier transform. And if you cannot see, I can write this integral more carefully for you. Just the integral part. Okay, e to the plus j omega minus omega naught t, and then I put that back inside. Dk over d omega z. I'm just collecting term and rewrite the exponent. Okay, can you see that? Hence, this thing is just a function of this, which is a function of this. Okay, but what else can I say? This integration is only going to be integrated over a narrow band of signal. Okay, it is going to be integrated over a narrow band of signal, which is what I also draw here, which I also draw over here. And if you integrate the Fourier transform over a very narrow band of signal, okay, the integration is over omega minus omega naught. This is essentially a Fourier transform integral. Let me call this tau. Okay, let me call this part tau. And then it's going to be over a very narrow bandwidth of signal. Okay, maybe I can call it the V naught, let me call it W of omega. Okay, this is going to be an integral, but only over a small number of omegas because of the narrow bandwidth of the signal. So from your course in Fourier transform, in this integration, if omega is only over a small number of values, what do you know about this as a function of tau? If you do a narrow band integration of a signal, okay, you're collecting only very small number of signals around omega equals omega naught. What can you say about this function? Anybody? See, all the integrations that you have is for omega approximately equal to 0. Okay, because I'm going to integrate this, and I'm going to only integrate this function for omega approximately equal to omega naught. Okay, because it's a narrow band signal. And so I can cast my Fourier transform integral to be something like that. And if you were to do this Fourier transform, where omega always has only small numbers, what can you say about f of tau? Anybody? Does anybody want to volunteer an answer? So can you follow all the manipulations so far? That you can go from that thing over there that you have into something that looks like this. And then when I integrate this, this just become a function of t minus dk omega dz. But this has to be, what I'm trying to get at is that this has to be a slowly varying function, because it's a Fourier transform of a signal that involves only small capital omega. And W, which is this function redefined, is only defined around omega or capital omega equal to 0. So this has to be a slowly varying function of tau. Can everybody see that?
Slowly varying comparing to omega, right?
It's in the time domain now. If I look at this function, if Fourier transform this function back to the time domain, and I'm only collecting capital omega values around small values. Okay. f of tau would be a slowly varying function of tau. Can you see that?
Yeah, I see.
Okay, very good. So f of tau is a slowly varying function of tau because of the narrow band integration involved. But outside this function, there is a rapidly varying function of t as well, a rapidly varying function of z. So this is the carrier part, okay? Whereas this one is the envelope. So what you have here is that we have a capital F that defines the envelope, and you have this carrier outside, okay, that defines the carrier inside the envelope. Okay, so some of you who are very clever might imagine or ask, this is not a real signal. Shouldn't this thing be real? Okay, well, you're saved by this, by the fact that when you Fourier transform a signal like this, you have a part that is in the real frequency part or positive frequency part plus a part that is in the negative frequency part. If you add the two of them together, this function will become real. Okay, these are very complicated knowledge of Fourier transform and signal analysis. But since you're electrical engineers, I hope that you might have them before. Okay, so any questions regarding this? I have them written out in greater detail in the lecture notes. Okay, again, I'm showing you a picture that I have said before, is that k is usually a very complicated function of omega for all wave-guided mode. But for the Fourier transform, you can assume that the signal to be narrow band, and then you can do approximation of the Fourier transform to arrive at something that is an envelope multiplying a carrier. Okay, that's what I'm trying to get at. Any questions so far?
Professor, I'm wondering about the shape of that function f of tau that you say slowly varying.
Yes, yes.
Draw it.
Yes. Do you know why this is slowly varying?
Yeah, I guess just because the integrand function is slowly varying. And
not integrand function, the integral. Your Fourier transform something with all the values close to DC, close to zero frequency. And hence the Fourier component of this function only consists of low frequency component of this integral. And hence it has to be slowly varying. Okay. These are intuition about Fourier transform that you should develop. Say if I have something that is broadband, okay, if I were to Fourier transform this to find its time domain equivalent, it will be rapidly varying. Okay. The Fourier transform of this will be rapidly varying. However, if I have a Fourier transform of a something in the frequency domain that is, say if I have a signal that is very narrow band in the frequency domain, in the time domain, this thing will be slowly varying. Okay, that kind of intuition you should develop. Okay, because you are linear superposing low frequency components. What is the Fourier transform integral? A Fourier transform integral is nothing but the sum of sinusoidal function. Okay, sum over this, and then reconstitute the time domain function. So if your Fourier signal only consists of low frequencies, in the time domain, it has to be slowly varying. Can you catch the point?
yeah, now the intuition is clear. Thank you.
Yeah, okay. So you go and revise your knowledge about Fourier transform theory, which as all good electrical engineers should have learned that as an undergraduate course as well, okay? So let's move on then. Let's move on to studying wave guidance in layup medium. And before I do that, I like to rewrite the generalized reflection coefficient again for you. Okay, I say that just like transmission line theory, I can define a generalized reflection coefficient that looks like this. One plus R12 R23 tilde e to the minus 2j beta 2z L2. And let's assume that this is L2, okay? And I can derive this using transmission line theory by mathematical homomorphism. The formula should be the same. And you can actually extract very interesting physics out of this reflection coefficient. I can do that by rewriting this as using a trick. Okay, R12, and then maybe 1 plus R12, R23. Now let's assume that R12 here is our, sorry, this should be 23. Let's assume that R23 is just R23, which means that they are just local reflection coefficients, okay? That means I don't have the fourth interface as this diagram over here. Then if I were to rewrite this as e to the minus 2j beta 2z L2, okay, and then subtract it out again. Subtract it out so that I have 1, 2, R12, R23, e to the minus 2j. J beta 2z L2 e to the minus 2j beta 2z L2. And then I have this term that I have to put it back in. Okay, I have to put as adding or subtracting a term. And then I have to not to forget the term that I have to put it back in. Okay, so if I look at the first term now, it is just R12 because this one divided by this term just give me R12. And then if I look at the terms I have left in the numerator, it will be something like R23 e to the minus 2j beta 2z L2. I take this term and take this term and put it outside. And then what I have is R12, R12. Okay, divided by this. 1 plus R12, R23 e to the minus 2j beta 2z L2. And you recall that the Fresnel reflection coefficient are given this way. Rij, if I just look at the TE case, Rij is beta Iz over mu I divided by beta Jz over mu J over beta Iz over mu I plus beta Jz over mu J. This is, we have an Ij interface. This is the Fresnel reflection coefficient. And you can see quite easily that if I were to sort I and J, the reflection coefficient just change sign. Okay, just change sign. So I can actually write one minus R12, which is this factor I have there. Okay, this factor I have there has been equal to 1 minus R12 squared, which is 1 plus R12 times 1 minus R12. Okay, and you probably recall that when we mesh boundary condition, 1 plus R12 is T12. Okay, in general, 1 plus Rij is Tij. The transmission coefficient are related to the reflection coefficient. That way, using this fact, I can replace this with R21. Okay, plus R21. And hence this factor can be written as T12, T21. Because this is just T21. This is just T12. So what I'm trying to get at is that this reflection coefficient, the second term, can be written more simply as, let me write it down here. R12 tilde is just a simple local reflection coefficient R12 plus T0, T12, T21, R23 e to the minus 2j beta 2z L2 divided by the denominator 1 minus R21 R23 e to the minus 2j beta 2z L2. Okay, very complicated stuff, but what am I trying to get at? What I'm trying to get at is that you can expand this into array series, and for instance, if there's no R23, if R23 had been 0, if R23 had been 0, then I will only have the first term. The first term would be the reflection coefficient from the first interface. And then the next term in the series, you can expand this into a power series, 1 over 1 minus x into 1 over plus x squared plus x cubed plus x4. You can expand this in the power series and look at each term of the power series. Okay, you'll find that the first term is just this picture over here. The second term, if you were to trace the physics of it, would be this term over here. And then if you look at the third term, it will be this term over here. You can actually do ray tracing and figure out every term of this series. This is called the ray picture or geometrical optic series. Okay. Okay, but what happens is that what I want to get at is that this formula does have a lot of physics in it. If you care to tease out the physics, okay, it looks very complicated, but if you go and tease out the physics, actually it has a very nice ray picture interpretation. But there's another physics that's buried in this reflection coefficient, which is that what happens if the reflection coefficient goes to infinity? Well, we saw that in the surface plasmon mode. When the reflection coefficient goes to infinity, what it means is that no incident wave gives rise to a reflected wave. You only need 0 incident wave, and yet there's a reflected wave. That means that there is a guided mode in the structure. The surface plasmon mode was guided due to that reason. You don't need an incident wave, and there is a reflected wave there. And it's the same as saying that you don't need a driving term in your equation. You will have a solution. That is called a homogeneous solution in a PDE or ODE. Okay, ODE, PDE, we call this a homogeneous solution. And then if you were to do matrix theory, Okay, then what we have then is that we have, if AX equal to B, let me see. Is equal to B, if B is equal to 0, then you have to solve this equation, and this is called a null space solution. Okay, those are all the same thing. And so if you want to look for the guided mode for this problem, one way to do it is to look at the reflection coefficient. Okay, when would this reflection coefficient go to infinity? Can anybody tell me when would this reflection coefficient go to infinity? It will go to infinity if the denominator goes to 0, just like the surface plasmonic case. Surface plasmonic case, we say that R12 Tm was given by something like beta 1z over epsilon 1 minus beta 2z over epsilon 2. And then we have beta 1z over epsilon 1 plus beta 2z over epsilon 2. And if the denominator goes to 0, we have the guidance condition for the SPP, surface plasmon polariton. Similarly, in a layered medium, if we have the denominator going to 0, then we would have a guided mode in the structure. So guidance occurs when 1 plus R12, R23 e to the minus 2j beta 2z L2 is equal to 0. Okay, is this clear to everybody? I'm just drawing the analogy of the surface plasmonic waveguide. By setting the reflection coefficient to 0, you can actually find the guidance condition and use that to find the guided mode in the structure. Okay. This thing is also called the transverse resonance condition. Okay. Let me see. So then, and so if you have a dielectric slab waveguide, for instance, one way to look for a waveguide mode is to think of this as a problem when you have an incident wave and the reflected wave. The wave just bounces around inside. Okay, and that guidance occurs when the incident wave is equal to 0. Okay, when the incident wave is equal to 0, and yet there's a reflected wave. That is what happens when a waveguide mode exists. Okay, and I said before, that is given by 1 plus R12, R23. In the general case, if this is more than 2 layers, you will put the R23 tilde over there, e to the minus 2j beta 2z L2, where L2 is the thickness of this region. Okay, and this is very similar to the homogeneous solution of a PDE or ODE and the null space solution of a matrix problem. Okay, so let's see if we can see more physics out of this. Why does this matter and what does it mean? And you can actually do ray tracing to understand this as well. And we can actually start out with, say, a wave say, let's start with the layered medium, a two interface problem where we have 1, 2, 3. And then we assume that the wave bounces in one of the interfaces, okay? And that you'll be reflected once, and then you will bounce back again, okay? And then it will be reflected at the second time around when it comes around. And what this equation says, which is the transverse resonance condition, what it's saying is that if a wave is to be guided, this has to also zero, but it also has other physical significance. It says that if the wave amplitude starts with 1, the first time it bounces around, it has an amplitude of R12 after bouncing around once, okay? And then it's going to propagate through the waveguide, and after propagation through the waveguide, it's going to acquire a phase. The phase is going to be beta 2z L2, just one, again, just one phase. Because as you know, in the time domain, or in the frequency domain, a propagating wave is expressed by this expression. So as z increases, it acquires a negative phase. So by the time it gets over here, okay, the wave will have e to the a phase of 2zL2. Okay, we'll have an amplitude of R12 and then acquiring an additional phase. Okay, and then if it bounces up once more time, it will be reflected by R23, R12 e to the minus j beta 2zL2. Okay, so by the time it bounces off the 2-3 interface one time, there will be its amplitude. And then it's going to travel. As it travels, this is my z-axis, and it's going to acquire a phase. The phase that they acquire there would be the same as this one, but very similar to that. And then, so the phase that it acquires then will be R23, R12, e to the j minus 2j beta 2z L2 now. Because it travels the thing 2 times, so the phase is 2 instead of 1, okay? Previously it was just 1 here, but here is now 2, okay? So this wave here should be in phase with this wave. If there's going to be guidance, okay? These two waves have to be in phase, which means that they have to be equal to 1. Okay, this has to be equal to 1. And this is precisely what this guidance condition says. Okay, I'm missing a sign error, right? I'm missing a sign error because the reflection coefficient I have here is quite wrong. Okay, if this is medium 1, this is medium 2, this is medium 3. What reflection coefficient should I use there? Anybody? If the wave is traveling,
Should be 2-1.
Yeah, R21. Okay, this should be R21. So it should have a minus sign here. Very good. R21. The reflection coefficient I should use at the first interface is R21. And over here, it should be a minus sign here. It should be R23. Okay. And then before it bounces there, the 2 should be in phase again. So I should have a minus sign here. And then I get back this equation precisely. And this is called the transverse resonance condition. Okay, any questions so far?
I have a question. Is this similar or the same thing as total internal reflection?
No, it's not the same as total internal reflection. In order for the wave to be guided, you will find that in order for this to be the same as each other, okay, this is a guidance condition. I have not mentioned total internal reflection yet, but if you're smart, you stare at this equation or stare at this equation. This equation can never be satisfied unless the amplitude of R23 and R12 are 1. And that happens only when you have total internal reflection, okay? If you look at this equation, it can never be satisfied unless amplitude of R23 and R21 are both 1. And that happens only at total internal reflection, okay? Okay, so since I have some time left, maybe I can go back and regurgitate on what we have learned in this lecture, okay? And so first we use mathematical homomorphism, that the plane wave traveling in layered medium is very analogous to the transmission line problem, especially the one interface problem. We show that this problem maps to this problem mathematically. So once you know how to find the reflection coefficient of this problem, you can use the same mathematical analogy to find the reflection coefficient for this problem. And again, you can show that this problem that I have here maps mathematically to the transmission line problem, a 3-section transmission line problem or 2-junction transmission line problem. Again, you can use mathematical homomorphism. If you know how to find the reflection coefficient of this structure, you know how to find the reflection coefficient of this structure, okay? And that we have already learned how to do it in transmission line theory, that if you have a multi-sectional transmission line, you just use this formula recursively. You can start with this and then work backward, and then find the generalized reflection coefficient at the 1-2 interface. And then you can apply this mathematical homomorphism to arrive at a similar formula for plane wave reflection in the layered medium. The reflection from the first interface is homomorphic to the reflection from the multi-section transmission line. And hence you can use this formula to calculate reflection coefficient from any layered medium, okay? The difference here is that this R12 that we have is the local Fresnel reflection coefficient. R12 tilde is a generalized reflection coefficient. The difference between generalized and local is that generalized includes reflection from behind the first junction, okay? Because these are actually reverberation from behind the first junction, okay? And then you can use this kind of structure to design filters in optics, like Fabry-Perot resonator. You can also use that to design filters at microwave frequencies, okay? So having learned how to solve this, we can actually solve quite complicated layered medium problem using transmission line analogy. And then we are ready to study the waveguide problem. The waveguide problem is actually, as we saw just now, was obtained by setting the denominator of this thing to be 0. And then you get the rather complicated wave guidance, where this beta x is a rather complicated function of omega, okay? We can define the phase velocity very easily. If we have a monochromatic signal or CW signal, we can just convert this back to the time domain using phasor technique. We can see that this has to be the phase velocity. However, if the signal is not monochromatic, it's not CW, not time harmonic, you can only describe it using a wave packet, for instance. Then the wave packet can be thought of as being constituted from many frequency components, and each frequency component would propagate with a different velocity, okay? So in order to describe a velocity involving multi-frequency signals, a non-monochromatic signal, we have to define what is called a group velocity. The group velocity is given by this, And how do we derive the group velocity? Well, we can use Fourier transform technique by going through our fundamental knowledge of Fourier transform. And if you have a monochromatic or quasi-monochromatic signal, it will Fourier transform to this. And if the center frequency is different, it will Fourier transform to something like this, for instance, okay? And then, so we analyze the velocity of propagation of this wave packet by assuming that, well, if you have a signal in the frequency domain, you can always write it in this manner. And we have found this k of omega before for the surface plasmon polariton. We found this to be the case. It is actually a very complicated function of omega. So in order to analyze the velocity of propagation of this wave packet, we take this Fourier transform. We find the Fourier transform representation of this, where this is a narrow band signal, and we plug in the approximation for k in the exponent of this thing. Okay, we plug in the exponent approximation for k. And once we plug in this Taylor series approximation, then the Fourier transform can be approximated by this function. And if you collect terms, it can be approximated by a rapidly varying term times a slowly varying term. This term is slowly varying by virtue of the fact that it's the Fourier transform of a narrow band signal. It's a Fourier transform of a narrow band signal, hence it has to be slowly varying, okay? So we can actually look at the velocity of this slowly varying part. It's actually the envelope. Okay, this part should be the envelope. And the envelope propagates with the velocity of dk over d omega. That's what we see. This envelope will propagate with the velocity of dk over d omega, which is the group velocity. And then the carrier will propagate with the phase velocity, okay? And we say that this is in general true. And then we go about and study the wave guidance in a layered medium. We say that we can actually find a waveguide mode very easily by staring at the reflection coefficient. But reflection coefficient has a lot of meaning in the sense that if you were to expand this using some mathematical manipulation, which is too complicated for me to do it slowly, so I did it very quickly. But it's just all algebra, okay, just algebra. And once you are able to do that, then you can show that this can be actually written as a geometrical series. And this reflection coefficient has this physical meaning, as you can see from this picture over here. And because of that, then if we want to look for a guided mode of a structure, we want to set the reflection coefficient to infinity, because what it means is that no incident wave gives rise to a reflected wave. That's what reflection coefficient equals to infinity means. That is the same as having a solution to an equation with no driving term, okay? Or having a homogeneous solution to an ODE or a PDE with no driving term, okay? And we did this for the surface plasmon polariton, and then for any general layered medium, this is the guidance condition for a wave in the layered medium, and this is called the transverse resonance condition. And then we want to give this transverse resonance condition physical interpretation. It can be traced to the fact that this equation is true because of phase coherence. If you start out with a wave with amplitude 1, after double bouncing, after bouncing once here, bouncing down here, when it reaches this stage, it has to be of the same phase as a wave over here. That's why we have this transverse resonance condition. And this would be the guidance condition for a waveguide mode in a layered medium. Okay, and next lecture I will go into the generalized thing and talk about this in more detail, and maybe dielectric waveguides, okay? Are there any questions before I quit?
Professor, I have a question.
Oh, sure.
So when we write the phase difference between for a round trip of the wave between two medias, we write it as beta z times L, which is the thickness of the material in z direction. Shouldn't we be able like write the phase difference as the general wave vector times the path the wave travels, like instead of just in z direction, it also moves along in another direction as well. So I'm kind of confused about
You're very correct about that. I ignore the phase change in the z direction or in the x direction. I ignore the phase change in this direction. I only keep track of the phase change in the z direction. It turns out that all the three waves varies the same way in the x direction by phase matching. Okay, if you were to keep track of the phases in this direction, they all cancel out. They are all the same.
So we can ignore that.
We can ignore them because by phase matching, they have to be the same. So I only keep track of the phase in the z direction when I do this study. That's a very good question because that is something that is puzzling a lot of students. Why didn't I keep track of the phase in the z direction? Because by phase matching, they're all the same. And I can cancel them out. Or I can ignore them, or I don't need to keep track of them.
Okay.
Okay. Very good question.
Thank you.
Any other questions? Well, then stop here and see you again on Thursday then. You have a good day. Okay.